This is a tutorial on completing the square. Completing the square is just another method for factoring a quadratic equation. Remember, if we have x squared plus bx plus c, and that factors into an x plus p times an x plus q, where p and q are just numbers, that would mean our b term is equal to p plus q, and our c term is equal to p times q. But what if we have a perfect square trinomial, where our quadratic equation factors into x plus p times x plus p, or an x plus p squared? Well, then our b would be equal to 2p, because it would be p plus p. And our c term would be equal to p squared, because it would be p times p. Well, if that's the case, that means our c then is equal to b over 2 squared. If I plug in 2p into this equation, I'll get c is equal to 2p over 2 squared. Well, our 2's will cancel and we'll be left with p squared. Well, that's what c is equal to. So if we have a perfect square trinomial, that means c is equal to b over 2 squared. So here, if I have x plus 8x plus c, and this was a perfect square trinomial, what would c equal to? Well, we can plug that into this equation again. We'd have c is equal to b over 2 squared. Well, our b is 8, so we'd have 8 over 2 squared. And 8 over 2 is 4, so this would be 4 squared, or 16. So our equation then would be x plus 8x plus 16. Now say we had an expression x squared plus 12x plus 36 is equal to 14. Well, this x squared plus 12x plus 36 is actually a perfect square trinomial. This would factor into an x plus 6 times an x plus 6. Or you could write that as x plus 6 squared. And this is equal to 14. So if we wanted to solve for our zeros or our roots, we could just take the square root of both sides. We'd have x plus 6 is equal to the square root of 14. But this would be in the absolute value sign because we have a square root of a square. Now if we want to drop the absolute value sign, we have to consider both the negative and positive versions. So we'd have an x plus 6 is equal to the square root of 14, and we have an x plus 6 is equal to the negative square root of 14. If we subtract 6 from both sides on both equations, we would get x is equal to a negative 6 plus the square root of 14, and x is equal to negative 6 minus the square root of 14. Or we could write that as x is equal to negative 6 plus or minus the square root of 14. But what if we had x squared plus 6x is equal to 16? This is not a perfect square trinomial. But if we want to, we can make it a perfect square trinomial. Remember, if we have a perfect square trinomial, our c term is equal to b over 2 squared. So if my b is 6, that means that our c is equal to 6 over 2 squared. Well, 6 over 2 is 3, so this would be 3 squared, or 9. So our c would be 9. So if we have an x squared plus 6x is equal to 16, I could make the left-hand side of this equation a perfect square trinomial by adding 9 to it. But if I add 9 to that one, I have to add 9 to the other side. Because if I just add 9 to one side, I change the value of x. So I have to add it to both sides. And if I do that, I'll have an x squared plus 6x plus 9 is equal to 16 plus 9. Now, x squared plus 6x plus 9 is a perfect square trinomial because we made it that way by adding 9. So this will factor into an x plus 3 times an x plus 3. Or we can say x plus 3 squared. And that's equal to 16 plus 9, that's 25. Now if we wanted to solve for x, we would take the square root of both sides. We'd end up with the absolute value of x plus 3 is equal to the square root of 25, which is just equal to 5. Now if we drop the absolute value, we'd end up with an x plus 3 is equal to 5 and an x plus 3 is equal to negative 5. If we subtract 3 from both sides on both equations, we get x is equal to 2 and x is equal to negative 8. So our solutions then are 2 and negative 8. But we got these solutions from our factored form of our equation, which was this x plus 3 squared was equal to 25. And we got that factored form by forcing the left-hand side of our equation into a perfect square trinomial. So since we forced it into a perfect square trinomial, that's called completing the square.